Welcome, Axor, Galactic Observatory. Tonight, the journey moves gently into the vast hidden architecture of the Milky Way, a galaxy filled with mysteries that science is still patiently uncovering. Far beyond the familiar band of starlight, this story drifts through ancient stellar halos, invisible dark matter, restless spiral arms, star-forming clouds, the layered galactic disk, and the quiet but powerful black hole at the center of it all. Along the way, it reveals how collisions, hidden worlds, and forgotten cosmic events have shaped our galaxy across billions of years. This is not only a story about stars, but about memory motion and the slow unfolding of a cosmic home, still changing even now. Before settling in, please take a moment to like the video, subscribe to the channel, and join Axor, Galactic Observatory, for more calm journeys through space science and the deeper wonders of the universe. Far beyond the bright spiral arms that most pictures show, the Milky Way opens into a quieter region, thinly populated and easy to overlook. This is the outer halo, a vast and dim realm surrounding the visible disk, stretching far into darkness, where stars become sparse, and the galaxy seems less like a shining wheel and more like a scattered memory. Here there are no bright lanes of gas, no crowded star fields, no obvious spiral design. Instead, there are ancient stars, old clusters, faint stellar remnants, and long drifting paths that take millions or even billions of years to complete. The outer halo is not empty, but it is patient. It holds objects that move on wide, tilted orbits, often far above or below the galactic plane, tracing out the shape of a galaxy that extends much farther than ordinary sight suggests. Some of these stars may lie tens of thousands of light-years from the center. Others are much farther still, wandering at distances so great that they define the Milky Way less by brightness than by gravity. They are dim sentinels at the edge of a much larger structure, marking where the familiar gives way to the almost unseen. The stars here are often very old. Many contain few heavy elements, which means they formed early, before repeated generations of stellar birth and death enriched the galaxy with carbon, oxygen, iron, and other materials forged in stars. In astronomy, these heavier elements are called metals, even when they include substances that would not be called metals in ordinary life. A star poor in such elements preserves a record of an earlier universe, one in which matter was simpler and the cosmos had not yet been thoroughly processed by time. Because of that, halo stars are not merely distant points of light. They are archives. Their chemistry carries clues about conditions that existed billions of years ago, when the Milky Way was still gathering itself from smaller fragments and early clouds of gas. Some may even be older than the galaxy's settled disk, formed in small ancestral systems before being carried into the larger structure that would become our galactic home. In the outer halo, age is not hidden. It is written into motion, composition, and isolation. Globular clusters also dwell in this realm. These are dense, roughly spherical collections of stars, often containing hundreds of thousands of members bound together by gravity. They orbit the galaxy like ancient companions, some of them nearly as old as the Milky Way itself. Seen from afar, a globular cluster is a concentrated lantern in the dark compact, and calm though inside it, stars crowd together much more tightly than in the region around the Sun. These clusters are valuable because their stars often form around the same time, making them useful records of early galactic history. Yet even they do not tell one simple story. Some globular clusters may have formed with the Milky Way, while others may have arrived from smaller galaxies later absorbed by it. That makes the halo a place of mixed origins. Not everything at the edge begins at the edge. Some things are born elsewhere and only later join the larger whole. White dwarfs, the cooling remains of once ordinary stars, are found here as well. They are stellar cores left behind after stars like the Sun exhaust their fuel and shed their outer layers. Faint and slowly fading, they can survive for immense spans of time like embers that refuse to disappear. Their presence in the halo points to very early generations of star formation, older than much of the thin disk that dominates the galaxy's bright appearance. Even when their original light has long softened, they continue to exist as evidence that the Milky Way's history did not begin with the shape it has now. The halo remembers earlier stages when structure was rougher, growth was less orderly, and the galaxy had not yet settled into the familiar pattern of bar bulge and spiral arms. Distance in the outer halo is difficult to grasp. Stars there are so remote and so widely separated that no naked eye view from within the galaxy could reveal the whole region clearly. Astronomers must infer its structure through careful mapping, measuring motion, brightness, and chemical composition. Variable stars help with this work. These are stars whose light rises and falls in a regular way, and for some types that rhythm reveals their true brightness. Once the true brightness is known, distance can be estimated by comparing it with how bright the star appears from Earth. In this way, a faint pulse becomes a measuring tool. Modern surveys, especially the Gaia mission of the European Space Agency, have transformed this picture by tracking the positions and motions of enormous numbers of stars with extraordinary precision. With such data, the halo no longer appears as a vague fringe. It begins to show texture, asymmetry, and structure. It reveals stars moving in tilted groups, remote clusters following ancient paths, and hints of debris left by events long past. The outer halo also shows that the Milky Way is not perfectly balanced. Its shape is subtly uneven. Some regions are denser than others. Some stars move in ways that suggest earlier disruptions. This lopsidedness likely reflects the galaxy's long history of gravitational encounters and mergers. Even at the far edge, the signs remain. The halo is quiet, but it is not simple. It is a place where the galaxy's oldest material and deepest scars remain lightly suspended in darkness. To look outward into it is to move backward in time toward a less finished Milky Way. There, beyond the bright disk, the galaxy becomes less a shining object and more a record of assembly survival and slow accumulation. The outer halo is the Milky Way's dim perimeter, but also its long memory, holding ancient stars and clustered relics in a vast surrounding hush, as though the galaxy keeps its earliest chapters not at its center, but in the faint and distant margin where almost nothing glows and almost everything endures. Across the outer halo, some of the Milky Way's most revealing structures do not appear as fixed objects at all, but as long and delicate trails of stars stretched across space like pale rivers. These are stellar streams, thin remnants of smaller systems that drifted too close to the Milky Way and were slowly pulled apart by its gravity. A stream begins when a dwarf galaxy or a globular cluster follows an orbit around the larger galaxy and experiences tidal force, the difference in gravity between its near side and far side. That difference is gentle at first, but over immense spans of time it becomes decisive. Stars are loosened from the smaller system and begin to escape, some moving ahead of it along the orbit, others falling behind. Eventually, the original body may shrink, distort, or disappear almost entirely, while its former stars remain arranged in extended bands that preserve the path of the encounter. In the quiet outer halo, where the background is sparse and the timescales are long, these streams can persist as ghostly signatures of capture and destruction. They are not random. They are ordered traces of motion records written not in ink but in orbit. Each one marks a story in which the Milky Way does not simply shine, but grows by taking in smaller neighbors. Observations over the last several decades have shown that the halo is threaded with such remains. Some streams are broad and rich, the leftover bodies of disrupted dwarf galaxies that once contained millions of stars. Others are narrow and delicate, likely stripped from globular clusters whose stars were once tightly packed before being teased apart into graceful lines. The distinction matters because dwarf galaxies and globular clusters are not the same kind of object. A dwarf galaxy is a small galaxy in its own right, often containing stars of different ages and chemical compositions, and usually embedded in a halo of dark matter. A globular cluster is much more compact with stars that are often more similar in age and composition, and with little or no evidence for its own large dark matter halo. When their remains are found in the Milky Way, they act as different kinds of clues. One tells of galactic accretion, the capture of small galaxies by larger ones. The other reveals the fragile survival of dense star clusters in a powerful gravitational field. In either case, the result is the same in a broad sense. The Milky Way is shown not as a structure that formed all at once, but as one assembled piece by piece. This idea, now central to modern astronomy, is supported strongly by stellar streams. The galaxy builds itself hierarchically, which means small structures form first, and larger ones grow through repeated mergers and absorption. The outer halo is where some of the evidence remains least disturbed, allowing these events to be studied long after the original collisions fade from immediate view. One of the most important examples is the Sagittarius stream linked to the Sagittarius dwarf spheroidal galaxy, a small companion galaxy currently being torn apart as it orbits the Milky Way. Its stars wrap around the galaxy in enormous looping paths, demonstrating on a grand scale what tidal disruption looks like in action. The dwarf galaxy itself still survives in part, but it is diminished. Its shape altered, its stars being drawn away to join the larger system. This is not a sudden event. It unfolds over hundreds of millions to billions of years, slowly converting a once separate galaxy into extended debris. Other streams, less obvious but equally important, have been uncovered through large sky surveys and precise motion data. Their stars often share similar velocities and chemical patterns, allowing astronomers to identify them as related even when they are spread across enormous distances. Chemistry is especially useful here. Stars born in the same system tend to carry a related chemical fingerprint because they formed from the same reservoir of gas. By measuring the abundance of elements in a stream's stars, astronomers can distinguish whether those stars likely came from a globular cluster or a dwarf galaxy, and sometimes even reconstruct aspects of the parent system's history. Motion adds another layer. A stream does not merely occupy space. It moves through the galaxy in a way that reflects both its origin and the larger gravitational field shaping it. That means streams are not only fossils of past mergers, they are also tools for measuring the Milky Way itself. Because their stars follow long paths through the halo, they help trace the distribution of mass, including mass that cannot be seen directly. Their bends, widths, clumps, and gaps may reflect the influence of the galaxy's unseen structure. Some disturbances in streams may even offer clues about smaller concentrations of dark matter passing nearby, though the interpretation of such features remains an active area of research. Observations indicate that streams are sensitive probes of the galactic potential, which is the full gravitational landscape created by the Milky Way's visible matter and dark matter together. In that sense, every disrupted system continues to serve the galaxy, even after its destruction, its stars becoming measuring lines across the dark. These rivers of captured stars also reveal that the Milky Way's history includes major mergers, not only minor ones. One striking example is the event sometimes called Gaia sausage, or Gaia Enceladus, identified through data showing a large population of stars on elongated orbits, many of them with distinctive chemical properties. The evidence suggests that several billion years ago, the Milky Way experienced a substantial merger with another galaxy, one large enough to leave a deep mark on the halo and perhaps influence the development of the inner structure as well. The stars from that system are no longer gathered in one intact companion. They are dispersed, mixed into the broader halo, but still identifiable as a family through shared motion and composition. This is a powerful change in perspective. The halo is not a smooth shell. It is partly a graveyard of former galaxies. It contains survivors' fragments and long mixed populations from repeated acts of accretion. Even now, the process is not fully over. Small satellite galaxies continue to orbit the Milky Way, and some may eventually be further stripped or absorbed. The outer halo therefore records both completed and ongoing assembly. It is a place where the border between the Milky Way and its former companions becomes blurred. Over time, captured stars cease to look foreign. They become part of the host galaxy, yet their motions still betray their origin, preserving the quiet memory of their arrival. In the far halo, where space is dark and sparse, these stellar rivers remain among the clearest signs that the Milky Way is not only a home for stars, but also the result of many smaller homes, undone and folded into one larger, still-growing whole. Beyond the visible stars, beyond the dust lanes and glowing gas clouds, the Milky Way appears to rest inside something much larger and much harder to detect. This surrounding structure is not made of ordinary luminous matter. It does not shine, does not absorb light in the familiar way, and does not reveal itself through direct observation with ordinary telescopes. Yet the evidence for it is strong and repeated. Astronomers call it dark matter, a name that describes what it does not do more clearly than what it is. It does not emit light. It does not appear to interact strongly with ordinary matter except through gravity. And around the Milky Way, its gravitational presence seems to form an enormous invisible scaffold, one that extends far beyond the bright disk and helps hold the entire galaxy together. Without it, the visible structure of the Milky Way would be much harder to explain. The stars in the outer regions move too quickly for the amount of observable matter alone. The galaxy rotates in a way that suggests there is far more mass present than the star's gas-dust planets and stellar remnants can account for. This mismatch is one of the deepest clues in modern astronomy. When astronomers measure how quickly stars and gas orbit the galactic center, at different distances they expect a certain pattern. If most of the galaxy's mass were concentrated near the center, as most of the visible light is, then objects farther out should orbit more slowly, much as planets in the outer solar system move more slowly than those close to the Sun. But the Milky Way does not behave that way. Observations indicate that orbital speeds remain high, even at large distances from the center. This produces what is called a flat rotation curve, meaning the decline in speed that would be expected from visible matter alone does not appear. Something unseen must be adding gravitational pull across vast distances. That something is inferred to be dark matter. The idea is not unique to the Milky Way. Similar rotation patterns are found in many other galaxies, suggesting that dark matter is not a local oddity, but a widespread feature of cosmic structure. In the Milky Way, this invisible mass appears to form a halo, but unlike the stellar halo, it is much larger and much more massive. The luminous galaxy is only the inner glowing portion of a broader gravitational system. The disk, the bulge, the globular clusters and the halo stars all move within this unseen framework. Dark matter shapes the motions of satellite galaxies, influences the paths of stellar streams, and helps determine how the Milky Way formed over time. It is called a scaffold because it provides the gravitational backbone on which ordinary matter gathers. In the early universe, small concentrations of dark matter, likely pulled in gas, allowing the first stars and galaxies to develop. Over billions of years, these structures merged and grew, producing larger systems such as the Milky Way. In this view, dark matter does not merely surround the galaxy now. It helps explain why the galaxy could form at all in its present scale and structure. The exact nature of dark matter remains uncertain. Many possibilities have been proposed, from new kinds of particles to other modifications in the understanding of gravity, though the particle interpretation remains the most widely explored within standard cosmology. What is known is mostly indirect. Its presence is inferred through gravitational effects. In galaxies, these effects appear in rotation curves in the motions of satellite systems and in the behavior of hot gas in larger structures such as galaxy clusters. On cosmological scales, dark matter also helps explain how matter clumped together after the early universe emerged from its initial hot, dense state. Measurements of the cosmic microwave background, gravitational lensing, and large-scale structure all support the conclusion that most matter in the universe is not ordinary atomic matter. The Milky Way is therefore not unusual in containing much more invisible matter than visible matter. It is one local expression of a much larger cosmic pattern. Still, the galaxy offers a particularly valuable laboratory because it can be studied from within, using the motions of individual stars. Modern surveys have made that effort much more precise. The Gaia mission, along with other observational programs, provides detailed measurements of stellar positions and velocities across large portions of the galaxy. These data allow astronomers to estimate the gravitational field in different regions and refine models of the Milky Way's mass distribution. Stellar streams are especially useful because they act like long test lines moving through the halo. Their shapes and motions respond to the underlying gravitational field, including the contribution from dark matter. Satellite galaxies provide another check. Their orbits and survival depend on the total mass of the Milky Way, not just its luminous disk. By combining these lines of evidence, astronomers estimate that the galaxy's total mass far exceeds the mass of everything that can be seen directly. Much of that total is attributed to dark matter. Yet even with this broad agreement, many details remain open. The exact total mass of the Milky Way is still being refined. The shape of the dark matter halo may not be perfectly spherical. It may be somewhat flattened, elongated, or irregular, influenced by the galaxy's formation history and the distribution of ordinary matter within it. Some models suggest a smoother halo, while others allow for clumps or substructure. If such clumps exist, they may leave traces in the behavior of stellar streams or satellite galaxies. There are also unresolved questions at smaller scales, such as whether dark matter distributions in galactic centers are sharply peaked or more gently rounded. These are not minor technicalities. They relate directly to the properties of dark matter itself and to the complex interplay between invisible matter and the energetic processes of star formation, supernova explosions, and gas dynamics. The Milky Way's visible beauty can make it seem self-contained, as though the galaxy is defined by what glows. But the deeper picture is less intuitive. The shining disk is only a thin, bright interior suspended inside a much larger invisible structure. Stars move within a gravitational architecture they do not illuminate. Gas gathers and rotates under forces partly set by matter that never appears in the night sky. The halo of dark matter is silent, unlit, and still unknown in substance, yet it may contain most of the galaxy's mass. In that sense, one of the Milky Way's greatest secrets is not hidden behind dust or distance, but behind invisibility itself. The galaxy that seems so richly visible is in its true mass and reach dominated by something unseen, an enormous dark framework that holds the bright parts in place and extends far into regions where light grows thin and gravity continues on. Where the Milky Way's bright disk begins to thin its structure, does not end cleanly. The outer disk does not remain flat and perfectly circular like a carefully cut wheel. Instead, it bends, twists, and grows subtly uneven, as though the galaxy's outer edge is responding to forces that have acted on it over immense stretches of time. This region is known as the warped outer disk, and it reveals that even the parts of the galaxy that seem broad and stable are shaped by continual gravitational influence. A galactic disk is the large rotating layer where most of the Milky Way's gas dust and younger stars are found. Much of the galaxy's familiar spiral appearance belongs to this flattened structure. But farther from the center, the disk begins to depart from that simple geometry. One side may rise above the central plane, while another dips below it. The gas layer may curve differently from the stellar layer. The outer parts may also show asymmetries in density thickness and motion, making the disk appear lopsided rather than balanced. These features are not small errors in observation. They are part of the galaxy's true form. The warp has been detected in neutral hydrogen gas, which is especially useful because this gas extends farther than the brightest stellar populations and can trace the disk deep into its outer reaches. Measurements show that the Milky Way's gas disk bends upward in some directions and downward in others, forming a warped shape that becomes more pronounced with distance from the center. Stars in the outer disk also participate in this pattern, though not always in exactly the same way. This matters because gas is relatively responsive and can be stirred or bent more easily, while stars carry a longer memory of earlier orbital conditions. If both stars and gas show warping, then the effect likely reflects a sustained or repeated influence rather than a short passing disturbance. Several possible causes have been proposed, and more than one may be at work. One major influence is likely the pull of satellite galaxies, especially the Large Magellanic Cloud, one of the Milky Way's most massive nearby companions. Though small compared with the Milky Way, it has enough mass to disturb the galaxy's outer regions through gravity, especially over long periods. As it moves through the larger dark matter halo, it may also create a gravitational wake region of enhanced density in the halo that further tugs on the disk. In this picture, the warp is not caused only by the companion galaxy itself, but also by the response of the surrounding dark matter structure. The outer disk becomes a visible surface reacting to invisible motion underneath. Past encounters with other satellite galaxies may have contributed as well, adding to the disk's bending and unevenness. The galaxy's history is not one of isolation, and the outer disk is among the places where that history remains legible. Another possibility involves the way gas falls into the galaxy from the surrounding environment. The Milky Way does not exist in perfect separation from intergalactic space. Over time, gas from the larger cosmic web may drift inward, and if that material arrives with a direction misaligned from the existing disk, it can gradually torque or twist the outer structure. A torque is a turning effect, a force that changes the direction of rotation or orientation. In a galaxy, such influences act very slowly, but given enough time, they can alter the shape of large regions. If fresh material enters at an angle, the outer disk may begin to tilt or bend in response. This possibility connects the warp not only to satellite encounters, but also to continuing galactic growth. The outer disk becomes a borderland where the Milky Way meets its environment, not a sealed edge, but a flexible interface between the galaxy and the larger universe around it. The lopsidedness of the disk adds another layer to this picture. A perfectly symmetric galaxy would have matching distributions of mass and motion on opposite sides, but the Milky Way shows departures from that ideal. Some areas of the outer disk appear denser or more extended than others. The stellar distribution may show ripples or oscillations, as if parts of the disk have been gently shaken. Large surveys of stars have revealed vertical waves regions where stellar populations move up and down relative to the midplane, suggesting that the disk has been disturbed more than once. These patterns may be the aftermath of past passages by satellite galaxies or dark matter substructures, or the result of longer internal responses to the galaxy's bar and spiral patterns. It remains uncertain which causes dominate in each feature, but the general conclusion is clear. The outer disk is dynamic and historically marked, not still and perfectly settled. This is important because the disk is often imagined as the most orderly part of the galaxy, the place where stars orbit in neat paths around the center. That image is only partly true. Order exists, but it is layered over a continuing record of disturbance. The outer disk also helps define the visible extent of the Milky Way, though that extent is not sharply bounded. Stellar density gradually decreases. Gas becomes thinner, and the distinction between disk and halo grows less obvious. In these transitional zones, astronomers must rely on motion chemistry and structure to tell one component from another. Outer disk stars may have different compositions and orbital patterns from halo stars, even when they occupy similar large distances from the center. Some may belong to a flared disk, where the outer disk becomes thicker with distance, rather than simply remaining a narrow plane. This flaring can result from weaker gravitational confinement in the outskirts, allowing stars and gas to spread farther above and below the midplane. The result is a galaxy whose edge is not a clean boundary, but a gradual and complex change in geometry. Observations of these regions have improved greatly with radio surveys of hydrogen gas and space-based mapping of stellar motions. Together, they show that the Milky Way is not flat. In the simple sense, not symmetrical in every direction, and not finished in the way older textbook drawings once suggested. Its outer disk bends under external pulls, responds to infalling matter, carries waves from earlier encounters and blends outward into a wider halo. The warp is therefore more than a shape. It is evidence that the galaxy remains open to influence. Even in its broad rotating body, the Milky Way keeps the imprint of passing companions in visible mass and continuing growth. The farther outward the disk extends, the more it reveals that the galaxy's form is not fixed, but continually adjusted by a larger gravitational conversation, unfolding in slow motion all around it. Within the warped outer disk, the Milky Way begins to show one of its most recognizable features, though even here, the familiar image is more complicated than it first appears. Spiral arms seem from a distance like permanent luminous lanes winding outward from the central regions, fixed structures made of the same stars, held together in graceful curves. But observations and theory together indicate a subtler reality. The spiral arms are not rigid formations through which the galaxy turns like a painted wheel. They are better understood as patterns of enhanced density, broad regions where stars, gas, and dust become temporarily more concentrated as they orbit the galactic center. This idea is known as the density wave picture, though in practice the Milky Way may also include more transient and evolving spiral features. What remains clear is that the stars do not stay locked forever inside one arm. They move in and out of these regions over time, while the pattern itself persists or changes on a different rhythm. In that sense, a spiral arm is less like a permanent road and more like a slow traffic pattern in which material briefly gathers, lingers, and moves on. This distinction matters because it changes the meaning of the galaxy's visible design. The spiral pattern is not a simple outline drawn by stable matter. It is a dynamic architecture shaped by orbital motion gravity and the compressible behavior of gas. Stars in the disk orbit the center of the galaxy at different speeds, depending on their distance, a phenomenon called differential rotation. if the arms were made of fixed groups of stars that remained together permanently, this differential rotation would wind them tighter and tighter over time until the pattern became impossibly twisted. Because the Milky Way is billions of years old and still shows recognizable spiral structure, astronomers conclude that the arms must be maintained in a more flexible way. In the density wave interpretation, material moves through the arm, while the arm remains a zone of higher density. As gas enters such a region, it is compressed. That compression can help trigger star formation, especially in cold molecular clouds already close to collapse. The result is that spiral arms often contain bright young stars, glowing nebulae, and dust lanes, making them stand out clearly, even though the individual stars within them are only temporary participants. The arms are therefore places where motion and structure meet. They are not static decorations, but active zones in the life of the disk. In the Milky Way mapping, the spiral pattern is more difficult than in external galaxies, because Earth lies inside the disk, surrounded by dust that obscures long lines of sight in visible light. Astronomers must reconstruct the galaxy's structure using radio observations, infrared surveys, the positions of star-forming regions, and the motions of gas and stars. This work suggests that the Milky Way contains several major spiral arms, including the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the Norma arm, along with smaller features and spurs between them. The Sun resides in a minor structure often called the Orion Spur, or Orion arm, located between larger arms rather than within one of the most massive primary lanes. This local placement gives an intimate but limited view. It allows study of nearby star-forming regions and stellar populations, yet it also means the whole pattern must be inferred from many partial perspectives. The arms themselves are rich in gas and dust, and this is why they matter so deeply to the galaxy's continuing evolution. In the denser regions of the disk, enormous molecular clouds form, made mostly of hydrogen molecules, along with dust and traces of heavier elements. These clouds are cold by astronomical standards, which allows gravity to act more effectively within them. When a cloud or a dense part of a cloud becomes unstable, it can collapse and fragment, producing clusters of new stars. Massive young stars then begin to shape their surroundings quickly through radiation, stellar winds, and eventual supernova explosions. This means the spiral arms are not merely visible curves. They are regions where the disk renews itself, where gas becomes stars, and stars begin the processes that will later return enriched material back into interstellar space. The passage of gas through a spiral arm is therefore both structural and generative. It helps maintain the galaxy, not by preserving the same matter in one place, but by encouraging cycles of transformation. Yet the density wave idea does not explain everything on its own, and modern research suggests that spiral structure may vary from galaxy to galaxy, and even within one galaxy over time. Some spiral patterns may be long-lived and relatively coherent, while others may be more transient, formed and reshaped by instabilities in the disk, by the influence of the central bar, or by gravitational encounters with companion galaxies. In the Milky Way, the bar in the inner galaxy likely contributes to the formation and maintenance of spiral structure by channeling matter and shaping orbital resonances. A resonance occurs when motions line up in a repeating gravitational relationship, allowing small influences to build over time. Such resonances can help organize matter into large-scale patterns. The outer disk-satellite interactions and the broader dark matter halo may also influence how the arms develop. This means the spiral structure is not governed by a single mechanism alone. It is the visible outcome of several coupled processes acting across different scales. The arms also contain dust lanes that often lie just inward of bright star-forming regions. These dark streaks are not empty gaps, but dense concentrations of dust and gas that block visible light. In images of spiral galaxies, such lanes give the arms a textured appearance. In the Milky Way, they shape the sky from within, obscuring some regions and reddening the light from distant stars. Dust may seem minor compared with stars, but it plays a critical role in cooling gas and helping molecular clouds form. Without it, star formation would proceed differently. Thus, even the darkest parts of the arms are active participants in the galaxy's larger pattern. The spiral arms are often treated as the Milky Way's defining visual feature, and in a sense, they are. But their deeper meaning lies not in their shape alone. They reveal that the disk is alive with movement, compression, and reorganization. The arms are places where stars pass through, gas gathers clouds, collapse, and light briefly intensifies. They do not simply decorate the galaxy. They show how matter flows through it, how order can exist without rigidity, and how a great rotating system can hold a recognizable form, even while its contents are always in motion, always entering, changing, and moving on. Along the spiral arms and within the denser lanes of the galactic disk, some regions grow so cold and so thick with gas and dust that they become the Milky Way's great nurseries of stars. These are molecular clouds, vast accumulations of matter made primarily of hydrogen in molecular form, along with helium dust grains and small amounts of heavier elements left behind by earlier generations of stars. They are among the darkest large structures in the galaxy when viewed in visible light, not because they contain nothing, but because they are so rich in dust that they block the light from what lies behind them. In infrared and radio observations, however, they appear as immense reservoirs of raw material, sometimes stretching across dozens or even hundreds of light years. Within them, the Milky Way quietly prepares its next generation of suns. These clouds are cold by the standards of interstellar space, often only a few tens of degrees above absolute zero. That low temperature matters because hot gas resists collapse, while cold gas can be compressed more easily under gravity. Inside a molecular cloud, turbulence, magnetic fields, external shock waves, and the cloud's own gravity all interact. The cloud is not still. It contains filaments, knots, cavities, and denser cores where matter slowly gathers. Over time, if one of these denser regions becomes heavy enough and sufficiently shielded from disruptive pressure, gravity can begin to win. The core contracts, growing denser and warmer as material falls inward. This is the beginning of star formation, not as a sudden ignition, but as a slow inward settling that may take hundreds of thousands of years before a true protostar, a forming star still gathering mass, becomes established at the center. The process is hidden from ordinary sight because the dust that helps make star formation possible also conceals its earliest stages. Infrared telescopes and radio instruments are needed to peer into these cradles of collapse. What they reveal is not one star at a time, but often many. Molecular clouds tend to fragment, which means they break into smaller, dense pieces rather than collapsing as a single whole. As a result, stars are commonly born in groups or clusters. Some clusters remain loosely bound for a time before their stars drift apart. Others stay together longer. In especially massive star-forming regions, very large stars may appear burning hot and bright and living short lives that quickly transform the cloud around them. Their intense ultraviolet light ionizes surrounding gas-stripping electrons from atoms and creating glowing regions known as emission nebulae. These nebulae shine in striking colors in photographs, but beneath the beauty is a forceful physical change. Radiation pressure, stellar winds, and later supernova explosions begin to erode and sculpt the parent cloud, dispersing some material while compressing other parts. In this way, star formation can both end and trigger itself, clearing away gas in one place while helping new dense pockets form nearby. The nursery is never passive. It is shaped by feedback, a term astronomers use for the way newborn stars alter the conditions that produced them. The Milky Way contains many famous stellar nurseries, though from inside the disk they are often known through fragments of view rather than as one complete panorama. The Orion molecular cloud complex is among the nearest and best studied. It contains dark dust lanes, active star-forming regions, young clusters and protostellar objects at many stages of development. Because it is relatively close, it offers an unusually detailed look at the physical steps involved in the birth of stars and planetary systems. Other giant star-forming regions across the galaxy, such as the Carina Nebula, the Eagle Nebula, and the Lagoon Nebula, show related processes on different scales. In these places, towering columns of gas, bright ionized fronts, and embedded young stars reveal the tension between collapse and disruption. The shapes can appear dramatic, but the underlying pattern is consistent. Cold, dense gas fragments. Gravity draws matter inward. Protostars form. Radiation and winds from the most massive newborn stars begin changing the cloud. Some material is blown away, some is compressed. Over millions of years, the cloud that gave rise to a stellar generation is partly consumed and partly dispersed. Dust plays a crucial role throughout this process. Though it makes up only a small fraction of the total mass, dust helps cool gas by radiating energy away, allowing collapse to continue. Dust grains also provide surfaces on which simple atoms can meet and combine, aiding the formation of molecular hydrogen and more complex molecules. In the densest environments, a rich chemistry develops, including water carbon monoxide, ammonia, methanol, and many organic compounds. This does not mean life is present, but it does mean the raw chemical ingredients for later planetary complexity begin to gather early, even before stars fully emerge. Around many protostars, rotating disks of gas and dust appear. These protoplanetary disks are the environments from which planets, moons, asteroids, and comets may later form. So, within the galaxy's stellar nurseries, the processes that eventually lead to planetary systems begin alongside the birth of stars themselves. The Milky Way is not only making light in these regions, it is also preparing worlds. Not all parts of the disk form stars equally. Star formation is concentrated where dense gas is available, often along spiral arms, but the details depend on local conditions. Magnetic fields can slow collapse. Turbulence can either support clouds against gravity or help create dense filaments that encourage it. Shock fronts from earlier supernovae may compress gas enough to initiate new collapse, though the exact effect depends on timing and environment. It remains uncertain in many individual regions which influence is dominant at a given moment. Observations indicate that star formation is both regulated and inefficient. Only a small fraction of a giant molecular cloud's mass may end up in stars before feedback disperses the rest. This inefficiency is important. If all the gas in such clouds collapsed at once, galaxies would consume their fuel much too quickly. Instead, the Milky Way forms stars gradually over long periods, sustaining renewal without exhausting itself immediately. In these quiet nurseries, hidden behind curtains of dust and spread across the disk in uneven concentrations, the galaxy carries out one of its most important tasks. It turns cold, diffuse matter into dense, glowing objects. It transforms invisible clouds into stars that will later shape the disk, enrich the gas with heavier elements, and perhaps host planetary systems of their own. The nurseries are therefore places of beginning, but also part of a cycle already underway, long before any one cloud forms. Matter arrives from earlier generations, of stars cools, gathers, darkens, and collapses. Then light returns. Within the Milky Way's broad rotating body, these clouds are the places where the future first takes shape, not in sudden brilliance, but in long, hidden intervals of compression chemistry and slow emergence inside the coldest and darkest folds of the galaxy. Between the bright stars and the dark molecular clouds, the Milky Way contains a broad and changing medium that fills much of the space across the disk. This is the interstellar medium, the diffuse mixture of gas dust, charged particles, magnetic fields, and radiation that occupies the regions between stellar systems. Though often described as empty compared with planets or stars, it is not truly empty at all. It is a dynamic environment through which matter circulates, cools, heats, compresses, and expands over immense spans of time. In this medium, the galaxy stores the raw material for future stars, while also receiving the remains of earlier generations. It is a place of exchange, neither as dark and dense as a molecular cloud, nor as concentrated and luminous as a star, but essential to both. The interstellar medium exists in several phases, each shaped by different temperatures, densities, and physical processes. Some regions are cold and dense, especially where atomic gas begins the transition toward molecular clouds. Other regions are warmer and more diffuse, containing neutral hydrogen that can be traced through its radio emission. Still others are ionized, meaning electrons have been stripped from atoms by energetic radiation from hot stars or violent events such as supernova explosions. There is also a very hot, thin component produced when shock waves heat gas to millions of degrees, creating large cavities and bubbles within the disk. These phases are not isolated layers. They overlap, mix, and influence one another. A cloud may be compressed by a passing shock, heated by nearby starlight, stirred by turbulence, or enriched by material expelled from dying stars. The space between the stars is therefore not calm in a simple sense. It is a restless fabric through which the Milky Way continually recycles matter. One of the main drivers of this restlessness is the supernova, the explosion that marks the death of certain kinds of stars. When a massive star exhausts its fuel, its core collapses and its outer layers are thrown into space with tremendous energy. The expanding debris moves outward as a shock wave plowing into surrounding gas and dust. This does several things at once. It heats nearby material, stirs turbulence, compresses some regions, disperses others, and injects newly forged heavy elements into the interstellar medium. Elements such as oxygen, silicon, calcium, and iron created inside stars or during the explosion itself are added to the galactic environment in this way. These materials later become part of new clouds, new stars, and eventually new planets. A supernova is therefore both an ending and a redistribution. It destroys the star's former structure while enriching the galaxy around it. Over time, repeated supernova explosions can carve out enormous cavities called superbubbles, especially in regions where many massive stars form and die in related clusters. These cavities may span hundreds of light years, filled with hot, thin gas and bounded by denser shells. They alter the flow of matter through the disk and help connect local events to larger galactic circulation. Stellar winds also contribute to this ongoing motion. Even before massive stars explode, they lose material through streams of charged particles flowing away from their surfaces. These winds can be strong enough to clear cavities in nearby gas shapes surrounding dust and add momentum to the local medium. Less massive stars also shed matter later in life, especially during giant phases, though more gently. Planetary nebulae formed when stars like the Sun expel their outer layers. Near the end of their lives, return carbon, nitrogen, and other elements to the surrounding medium. Over billions of years, such contributions build a chemical inheritance across the galaxy. The interstellar medium becomes steadily enriched, though never evenly. Different regions carry different histories of star formation feedback and inflow. This unevenness is important because it means the Milky Way does not evolve chemically in a smooth and uniform manner. It develops local variations, pockets of relative richness or poverty, shaped by both internal activity and larger-scale flows. Magnetic fields thread through this medium as well. They are invisible but significant, helping guide charged particles and influencing how gas clouds move and collapse. In some regions, magnetic pressure can oppose gravity, slowing the contraction of gas into denser structures. In others, the field becomes tangled with turbulence, participating in the complex shaping of filaments and clouds. These fields also affect cosmic rays, high-energy particles moving through the galaxy at nearly the speed of light. Cosmic rays are produced in energetic environments, including supernova remnants, and they contribute additional pressure and ionization to interstellar space. Though individually tiny, their cumulative role is part of the broader balance that determines how easily gas cools, collapses, or disperses. The interstellar medium is therefore not governed by gravity alone. It is a many-layered system in which thermal energy, turbulence, magnetic structure, radiation, and explosive feedback all participate. Dust, though only a small fraction of the total mass, remains central here as well. Dust grains absorb and scatter starlight, dimming and reddening the light from distant objects. This is why the Milky Way appears streaked with dark lanes, invisible images, and why some parts of the galaxy are so difficult to observe directly. Yet dust also protects molecules from harsh radiation, aids cooling, and supports chemical reactions on its surfaces. It contributes to both obscuration and creation. Without dust, the interstellar medium would behave differently, and the transition from diffuse gas to star-forming cloud would be harder to achieve. On larger scales, the interstellar medium participates in galactic fountains and circulation. Gas heated by supernovae can rise above the disk into the lower halo, cool, and later fall back toward the plane. This process helps redistribute matter and energy across different regions of the galaxy. At the same time, inflows from the halo or intergalactic environment may bring in fresh gas, adding to the supply available for future star formation. The Milky Way's disk is therefore not a sealed system. It breathes in a slow astronomical sense, sending material outward and drawing some inward again. Observations indicate that this circulation helps sustain star formation over long periods, though the exact balance between inflow, outflow, and local recycling remains an active area of study. What is clear is that the space between stars is not merely background. It is the medium through which the galaxy renews itself. In the interstellar medium, death and birth are linked. Old stars return matter to space. Explosions and winds stir that matter into new configurations. Clouds gather, collapse, and form new stars, which then begin the cycle again. The Milky Way's visible stars may attract the eye, but the quieter drama unfolds in the medium between them, where matter is never at rest for long, and the galaxy continually reshapes its own substance through shock cooling motion and time. Within the broad disk of the Milky Way, between its larger spiral arms, the solar system travels through a quieter region known as the Orion Spur, sometimes called the Orion Arm. This is not one of the galaxy's most massive primary arms, but a smaller structure between the Sagittarius Arm and the Perseus Arm, a local bridge of stars, gas, and dust that provides the immediate galactic setting for the Sun. From within it, the Milky Way does not appear as a grand spiral design. It appears instead as a band of diffuse light across the night sky, crossed by dark dust lanes and shaped by perspective from inside the disk. Yet this local region has a structure and history of its own. It is calm only in a relative sense. Compared with the most crowded and active zones of the galaxy, the Sun's neighborhood lies in a less extreme environment, away from the dense central bulge, away from the most intense starburst regions, and away from the strongest tidal disturbances. That relative quiet may have mattered. It places the solar system within what astronomers sometimes describe as part of the galactic habitable zone, a broad and not sharply defined region where conditions may be more favorable for long-term planetary stability and complex chemistry. This does not mean the galaxy has a clearly marked safe ring, nor that life is guaranteed where conditions are moderate. It means only that some regions appear less hostile than others. Very near the galactic center, stellar densities are high energetic events may be more frequent and gravitational perturbations are stronger. Farther out in the disk, the abundance of heavy elements may drop, reducing the raw material available for rocky planets and complex chemistry. The Sun lies in an intermediate region, about halfway from the center to the visible outer disk, where earlier generations of stars have already enriched the interstellar medium, but where the environment is less crowded and less violent than in the inner galaxy. In this sense, the solar system occupies neither an exceptional center nor a remote fringe, but a middle ground shaped by long galactic evolution. The local neighborhood contains a mixture of older stars, younger stars, faint red dwarfs, white dwarfs, open clusters, diffuse interstellar clouds, and pockets of recent star formation. Many of the nearest stars are smaller and dimmer than the Sun, which is itself an ordinary star by the standards of the galaxy. The surrounding region, often measured across tens to hundreds of light years, includes structures such as the local bubble, a cavity of relatively low density hot gas through which the solar system currently moves. This bubble is thought to have been carved by ancient supernova explosions, perhaps from nearby groups of massive stars that lived and died long before the present era. Its existence is a reminder that even a comparatively quiet neighborhood carries the imprint of earlier energetic events. The calm of the present does not mean the absence of past disruption. It means only that the immediate conditions now are less severe than those in more crowded or active zones. The Sun itself orbits the center of the Milky Way at a speed of roughly a few hundred kilometers per second, completing one full galactic orbit in about 200 million to 250 million years. This period is sometimes called a cosmic year. During its lifetime, the Sun has completed many such revolutions, moving through different portions of the disk-passing spiral structure, interstellar clouds, and changing stellar neighborhoods. The solar system is therefore not fixed in galactic context. It drifts through the larger rotating body of the Milky Way, carried by the disk, while also oscillating gently above and below the galactic plane. These vertical motions may take tens of millions of years per cycle. They are modest compared with the scale of the galaxy, but they mean the Sun's path is not a perfectly flat circle. It is a long and slightly undulating journey through a layered stellar environment. Some researchers have considered whether these motions might influence long-term conditions in the solar system through changes in nearby stellar density, cosmic ray exposure, or encounters with interstellar clouds. Ideas of this kind remain difficult to confirm in detail, and many proposed links remain uncertain. What is well established is that the solar system is part of a much larger orbital story, one that places Earth within a moving galactic setting rather than a stationary cosmic backdrop. The local region also reflects the chemical history of the Milky Way. The Sun contains more heavy elements than the oldest halo stars, because it forms much later from gas already enriched by previous generations of stellar birth and death. The rocky planets, metal-rich meteorites, and complex chemistry of the solar system depend on that inheritance. Iron, silicon, magnesium, oxygen, carbon, and many other elements found in Earth and its neighboring worlds originate in earlier stars and stellar explosions. By the time the Sun forms, the galaxy has already been recycling matter for billions of years. The local disk where this material gathers into new clouds and stars is therefore not only the Sun's physical neighborhood, but also part of its chemical ancestry. Every atom heavier than hydrogen and helium in the Earth's crust oceans, atmosphere and living systems reflects a galactic history older than the solar system itself. Yet the Sun's neighborhood is not simply moderate in radiation and rich in elements. It is also shaped by gravitational relationships on smaller scales. Nearby stars pass one another over immense times, occasionally close enough to disturb distant comet reservoirs, such as the hypothetical Oort cloud. Giant molecular clouds, though not common in the immediate present neighborhood, can influence stellar orbits if encountered. Spiral arms may bring somewhat denser and more active environments when crossed. Even in a relatively favorable zone, stability is only relative. The Milky Way does not offer a motionless refuge. It offers a range of environments through which stars travel, with some regions presenting fewer hazards than others across geological timescales. The Orion Spur is thus a local compromise, not a place of perfect safety, but a region where the balance of chemical richness and environmental calm appears to have allowed at least one planetary system to persist long enough for complex life to emerge. From inside this neighborhood, the galaxy can seem familiar, almost domestic. A field of nearby stars and dust clouds embedded in the wider disk. But that familiarity is limited by scale. The Sun belongs to a minor spur in one section of one galaxy among many. Its calm setting is the result of countless earlier processes, from the enrichment of interstellar matter to the shaping of the disk by spiral patterns, and the avoidance of more extreme inner regions. The local neighborhood is therefore both ordinary and quietly remarkable. A modest part of the Milky Way, where the long galactic balance between matter, motion and time has produced a setting gentle enough for worlds to remain evolve and continue their orbit within the larger turning structure of the galaxy. Among the many stars scattered across the Milky Way, some preserve a chemical simplicity that reaches back toward the earliest chapters of cosmic history. These are ancient stars, often poor in heavy elements, and they serve as some of the most valuable witnesses to the galaxy's formation. In astronomy, heavy elements are all elements heavier than hydrogen and helium, including carbon, oxygen, calcium, and iron. A star with very low abundance of such elements is described as metal poor, not because it is made of metal in the ordinary sense, but because it forms from gas that has not yet been enriched by many earlier generations of stellar birth and death. Such stars are important because the early universe contains almost no heavy elements at all. After the first few minutes of cosmic history, matter consists mostly of hydrogen and helium, with only tiny traces of lithium. Everything heavier is produced later inside stars or during violent stellar endings. This means a metal-poor star forms from relatively unprocessed material and may have originated when the Milky Way or one of its ancestral fragments is still young. By studying these stars, astronomers can trace how the galaxy gradually builds chemical complexity over billions of years. The oldest stellar populations are found most often in the halo, the globular clusters, and the thick disk, though some ancient stars also pass through the solar neighborhood on unusual orbits. Their ages are not measured with the ease of a clock. Instead, astronomers infer age through stellar models, chemical abundances, and evolutionary stage. A star's mass, temperature, brightness, and composition determine how quickly it changes over time. Very old stars that are still visible today tend to be low-mass stars because massive stars burn their fuel too quickly to survive for billions upon billions of years. The ancient stars that remain are therefore typically small and long, lived still shining long after more massive companions would have exploded or faded into compact remnants. Their survival makes them natural archives. Their atmospheres, especially in stars that have not been strongly altered by internal mixing, can preserve the chemical character of the gas cloud from which they form. This allows astronomers to use spectroscopy, the study of light broken into its component wavelengths, to measure how much of different elements a star contains. Each element leaves a distinctive set of absorption lines, dark features in the spectrum where specific wavelengths have been absorbed. By comparing the strength of these lines, astronomers can estimate relative abundances and reconstruct aspects of the star's origin. The results reveal not only age in a broad sense, but also ancestry. Some ancient stars appear to form in the Milky Way itself during its earliest growth. Others seem to have originated in dwarf galaxies, later absorbed into the halo. Chemistry helps distinguish these lineages because different star-forming environments enrich their gas at different rates and in different proportions. A galaxy that forms stars rapidly will build up some elements faster than a smaller system with slower and less efficient star formation. Thus, a star's elemental pattern can function almost like a birthplace signature, even after the star has wandered far from its original home. This is why galactic archaeology, the effort to reconstruct the Milky Way's past through stellar populations, relies so heavily on both motion and chemistry. Ancient stars are not just old. They are historically specific. Some of the most chemically primitive stars known contain extraordinarily small amounts of iron, implying that they form from gas, enriched by only one or a few earlier supernovae. In such cases, the star may carry the signature of the first generations of stellar explosions, perhaps even influenced by stars that belong to the universe's earliest population. Those first stars, often called population 3 stars in theoretical models, remain uncertain in direct observation. They are thought to form from nearly pristine hydrogen and helium, probably to be massive and short-lived, and therefore unlikely to survive to the present day. No unquestioned example has yet been observed directly. But some ancient metal-poor stars in the Milky Way may preserve indirect evidence of their existence through unusual chemical patterns. Observations indicate that certain abundance ratios in very old stars are consistent with enrichment from early massive supernovae. It remains uncertain exactly which pathways dominate in each case, but the broader implication is clear. The oldest stars alive today may carry within their light a partial record of stellar generations now entirely gone. The thick disk adds another layer to this chemical story. Compared with the thin disk where the Sun resides, the thick disk contains older stars with somewhat different motions and lower average metallicity. These stars orbit the galaxy with greater vertical extent, moving farther above and below the main plane. Their compositions suggest that the thick disk forms earlier, during a more turbulent period in the Milky Way's history. Some of its stars may have formed in place during that unsettled era. Others may reflect heating of an early thinner disk by mergers and gravitational disturbances. Their chemistry preserves the transition between the earliest halo-dominated assembly and the later, more orderly star formation of the thin disk. In this way, the galaxy's chemical record is layered not only by age, but by structure. Halo stars, thick disk stars, thin disk stars, and bulge stars each tell related but distinct parts of the same long history of enrichment. Globular clusters contribute another kind of memory. Although once thought to be chemically simple, some are now known to contain multiple stellar populations with subtle abundance differences, indicating that their formation histories may be more complex than once assumed. Still, many globular cluster stars remain among the oldest known in the Milky Way, and their ages help constrain when the galaxy's earliest large-scale structures emerge. Their presence supports the view that the Milky Way begins forming stars very early in cosmic time, then continues to grow through accretion, internal evolution, and repeated chemical recycling. Every generation changes the raw material for the next. Massive stars live briefly and enrich the surrounding medium quickly. Smaller stars contribute on longer timescales. Exploding white dwarfs in binary systems add iron group elements later still. Neutron star mergers likely contribute much of the heaviest rapid neutron capture elements, though the balance between such sources and certain supernova channels continues to be refined. The result is not a single smooth chemical rise, but a complex unfolding pattern in which different elements appear and accumulate at different rates. Ancient stars preserve the earliest points on that curve. They show the Milky Way before repeated generations of stellar processing fill its gas with the materials familiar to planets and life. They reveal a galaxy poorer in metals, rougher in structure, and closer to the elemental simplicity of the early universe. In their faint atmospheres, measured carefully through light, the past remains available. The Milky Way's oldest stars therefore act as a chemical memory, not because they remember in any living sense, but because they endure. They continue to shine long after the environments that formed them have changed or disappeared, carrying forward the composition of ancient gas and the imprint of long-vanished stellar ancestors. To study them is to read the galaxy before it becomes fully itself, when its light is thinner, its structure less settled, and its future complexity still only beginning to gather. Beneath the Milky Way's broad visible band lies a layered structure that only gradually becomes clear when the motions and ages of stars are studied in detail. The galactic disk is not a single uniform sheet. It is commonly described as having two main stellar components, the thin disk and the thick disk, each with different characteristic ages, chemical compositions, and orbital behaviors. The thin disk contains much of the gas dust and younger stellar population that give the Milky Way its active and familiar appearance. This is where the spiral arms stand out most clearly, where molecular clouds gather, and where new stars continue to form. The thick disk, by contrast, contains older stars that move on somewhat puffier orbits, traveling farther above and below the galactic plane. Its stars are generally poorer in heavy elements than those of the thin disk, and their motions suggest a different past one tied to an earlier and more turbulent phase of galactic development. These two layers are not sharply separated like stacked boards. They overlap and blend, but their differences are real enough to show that the Milky Way's disk has evolved in stages, rather than emerging all at once in its present form. The thin disk is comparatively narrow in vertical thickness, with most of its stars orbiting close to the midplane. Because it contains cold gas and ongoing star formation, it is the most visibly alive part of the galaxy. Open clusters, bright young stars, supernova remnants, nebulae and dust lanes all belong mainly to this component. Chemically, the thin disk reflects a galaxy already enriched by many earlier stellar generations. Its stars tend to contain more heavy elements than those in the thick disk or halo because they form later from gas that has undergone more extensive recycling. The Sun belongs to this thinner layer, which means the solar system is part of a comparatively mature stage in the Milky Way's development. Yet the thin disk is not static or entirely settled. Spiral structure passes through it. Molecular clouds form and disperse within it. Stars gradually migrate inward or outward over long timescales through interactions with spiral arms, the central bar, and other gravitational irregularities. This process, often called radial migration, means that a star's present location does not always match the place where it originally formed. Over billions of years, the disk slowly rearranges itself from within, softening some chemical gradients and mixing stellar populations that began in different parts of the galaxy. The thick disk presents a different character. Its stars are older on average, often several billions of years older than typical thin disk populations. They move with higher vertical velocity, which means their orbits take them farther from the midplane before gravity draws them back again. They also orbit the galactic center somewhat more slowly on average than thin disk stars. These differences suggest that the thick disk forms during a period when the galaxy is less orderly, more dynamically heated, and more strongly affected by mergers or internal instability. Several formation scenarios have been proposed. One possibility is that the thick disk originates from an early thin disk that is later stirred and heated by mergers with smaller galaxies, causing stars to occupy more vertically extended orbits. Another is that the thick disk forms rapidly from turbulent gas in the early Milky Way before conditions settle enough to produce the colder, flatter, thin disk. A third possibility involves accreted stars from satellite galaxies, contributing directly to the thickened population, though observations generally suggest that much of the thick disk forms within the Milky Way itself, rather than being composed mainly of foreign stars. The present view may involve a combination of these processes. What matters most is that the thick disk records an earlier galactic state, one in which the Milky Way is still assembling and settling after repeated disturbances. Chemistry supports this picture. Thick disk stars often show enhanced abundances of certain elements, especially alpha elements, such as oxygen, magnesium, and silicon relative to iron. This pattern suggests that their gas is enriched quickly by massive stars and core collapse supernovae, before longer timescale sources such as exploding white dwarfs in binary systems add as much iron to the interstellar medium. In simpler terms, the thick disk appears to form during a period of rapid star formation and swift chemical enrichment, while the thin disk reflects a longer, calmer, and more extended history. These abundance patterns make the two disk components easier to distinguish, even when their stars overlap in position. A star's chemistry and motion together can reveal which layer it most likely belongs to and what epoch of the galaxy's past it represents. Large stellar surveys have made this separation much clearer by combining precise motions, distances, and elemental measurements for millions of stars. From these data, the disk appears not as a monolithic structure, but as a historical archive written in layers of orbit and composition. The disk also shows vertical and radial gradients that speak to long internal evolution. Stars closer to the galactic center tend on average to be richer in heavy elements than stars farther out, reflecting stronger and more sustained star formation in the inner regions. Younger stars often remain closer to the plane than older stars, partly because they form from relatively cold gas, while older populations have had more time to experience heating through interactions and perturbations. Yet these broad trends are blurred by migration resonance and the gravitational influence of spiral arms and the central bar. The result is not a perfectly ordered system, but a complex one in which earlier structure is partly preserved and partly remixed. This ongoing reshaping means that even after the disk settles into recognizable layers, it continues to evolve. The Milky Way's disk is therefore both stratified and alive, holding older records in one component, while still producing new stars in another. The distinction between thin and thick disk also helps place the Sun in context. The solar system belongs to a layer that forms after the galaxy has already undergone major early assembly chemical enrichment and dynamic heating. Earth and the other planets arise not in the Milky Way's first chapter, but in a later era when the disk has become calmer and more metal-rich. The thick disk beneath and around that later stage is a reminder that this calmer environment is built on an older and rougher foundation. It preserves the memory of a time when the Milky Way's main body is still thickened by turbulence, disturbed by mergers, and chemically simpler than the disk familiar today. Seen in this light, the layered disk is not merely a geometric arrangement, it is a record of transition. The thick disk speaks of early intensity and dynamical stirring. The thin disk speaks of continued star formation, gradual mixing, and long-lived galactic maintenance. Together, they show that the Milky Way becomes habitable, structured, and chemically mature through sequence rather than sudden design. Its settled appearance rests on older motion, older stars, and an earlier phase that remains present, not as a separate galaxy, but as a thicker, older layer still orbiting within the same broad turning body. As the Milky Way's layered disk draws inward, the broad spiral structure gradually gives way to a more elongated and concentrated form that shapes the inner flow of stars and gas. This is the central bar, a long stellar structure extending across the galaxy's inner region, passing through the heart of the disk, rather than remaining round around the center. Barred galaxies are common in the universe, and the Milky Way is now understood to be one of them. Though this becomes clear only through infrared observation, stellar mapping, and the motions of gas and stars. Visible light alone cannot easily reveal the bar from Earth because thick dust lanes obscure the inner galaxy. From inside the disk, the central regions appear crowded and darkened, not easily resolved into large-scale geometry. But infrared light can pass through much of that dust, and when combined with measurements of stellar density and velocity, it shows that the inner Milky Way is not shaped simply as a circle. It contains an elongated bar that rotates through the central disk, channeling matter and influencing the galaxy far beyond its own length. A galactic bar is made primarily of stars, though gas and dust also respond strongly to its gravitational presence. It forms when the inner disk becomes dynamically unstable, allowing orbits to align in a stretched pattern rather than remaining mostly circular. Once established, the bar becomes a major organizer of motion in the inner galaxy. Stars within it follow elongated paths, and gas clouds moving through its gravitational field may lose angular momentum, which is the orbital tendency that keeps matter circling at a distance rather than falling inward. As gas gives up some of this orbital support, it can move closer to the center. In this way, the bar acts as a slow transport mechanism, guiding material from the inner disk toward the central regions. It does not drag matter inward like a rigid rod, but its rotating gravitational pattern creates preferred pathways and resonances that reshape the orbits of stars and gas over very long times. This makes the bar one of the most important structures in the Milky Way's internal evolution. It helps link the outer disk to the inner bulge and affects where star formation is enhanced or suppressed. The length and exact orientation of the Milky Way's bar have been refined over time as better data become available, but the general picture is well supported. The bar extends for several thousand light-years from the center and is tilted relative to the line connecting the Sun to the galactic center. This tilt means that one end lies somewhat nearer to the solar system's line of sight than the other, producing asymmetries in star counts that were once puzzling until the barred structure became clear. Observations of red clump stars, which serve as useful distance markers because of their relatively uniform brightness, have been especially important in mapping this inner shape. Gas motions also support the presence of the bar, because the inner disk does not rotate in the simple pattern expected for a purely axisymmetric galaxy. Streams of gas show evidence of non-circular motion, as though responding to a rotating, elongated potential rather than a smooth, round center. These signatures are exactly the kind of behavior a bar can produce. Once the bar is present, it affects the galaxy through resonance. A resonance in galactic dynamics occurs when orbital frequencies line up in such a way that repeated gravitational nudges reinforce one another over time. In the Milky Way, the rotating bar creates resonant regions where stars and gas respond more strongly to its influence. Some of these resonances may help shape spiral structure farther out in the disk. Others may create rings or concentrations of gas in the inner galaxy. Near the center, gas funneled inward by the bar may accumulate in dense regions where star formation becomes more active. This does not mean the bar alone determines the fate of all inner matter, but it acts as a powerful mediator, redistributing angular momentum and changing where material collects. The bar therefore helps convert a broad rotating disk into a more differentiated galaxy, one with an active inner structure distinct from its outer spiral form. It is part of the reason the Milky Way has a central bulge and inner molecular zone, rather than only a simple flat disk reaching all the way inward. The bar also changes over time. It may grow longer, slow its pattern speed, or interact with the surrounding disk and dark matter halo in ways that gradually alter its character. Some simulations suggest that bars emerge naturally in mature disk galaxies and evolve through exchanges of angular momentum with the disk and halo. This implies that the Milky Way's bar is not a permanent fixture present from the very beginning, but a structure that develops as the galaxy matures. If so, it becomes another sign that the Milky Way's present appearance is the result of long internal transformation as well as ancient mergers. The inner galaxy is not only a remnant of early assembly. It is also shaped by slower secular evolution, a term astronomers use for gradual change, driven by the galaxy's own internal dynamics, rather than by violent external collisions. The bar is one of the clearest engines of this slower remodeling. It redistributes stars, alters gas flows, and helps reshape the central regions over billions of years. From the perspective of the solar system, all of this is hidden behind dust distance and the difficulty of looking inward from within the disk. The galactic center lies in the direction of the constellation Sagittarius, but the true geometry of the inner Milky Way cannot be grasped by simple visual inspection. It must be reconstructed through wavelengths that pass dust more effectively and through careful dynamical modeling. This makes the bar a good example of one of the galaxy's hidden truths. The Milky Way may appear from imagination as a neat spiral with a bright center, but the actual inner structure is more specific and more complex. It contains an elongated, rotating bridge of stars, quietly shaping motions across thousands of light years. The bar is not merely a detail near the center. It is a mechanism of transport and transformation, a structure that channels gas inward influences, spiral patterns outward, and links the disk's broad rotation to the denser regions closer to the core. In this sense, the Milky Way's center is approached not through a circle, but through a stretched and rotating form, one that reveals how gravity organizes large systems not only by gathering matter, but by steering its flow into new patterns over immense spans of time. The bar is the inner disk becoming directional, the galaxy learning how to move material toward its heart without abandoning its larger rotating order. Inside the reach of the central bar, the Milky Way grows denser, brighter in infrared light, and more structurally intricate. Here the galaxy swells into what is known as the bulge, a crowded central concentration of stars surrounding the inner core. For a long time, bulges in galaxies are imagined as simple rounded spheroids, older stellar swarms piled around the center by early collapse or repeated mergers. The Milky Way does contain such an ancient central concentration in some measure, but its bulge is not merely a smooth ball. Observations indicate that it has a distinct three-dimensional shape, often described as boxy or peanut-shaped when seen edge-on. This unusual form is not a poetic comparison. It emerges from the actual arrangement of stars in the inner galaxy and reflects the dynamical history of the bar itself. Rather than being a separate rounded component, entirely independent of the disk, much of the bulge appears to be the thickened inner part of the bar, lifted into a vertically extended shape through long internal evolution. In other words, the Milky Way's bulge is not only ancient, it is also sculpted. The peanut shape develops through orbital changes in the bar over time. As the bar evolves, some of the stars in it begin to move on orbits that rise above and below the galactic plane in a more pronounced way, thickening the inner structure and creating a bulge that appears boxy or peanut-like when viewed from the side. Numerical simulations show that this kind of shape can arise naturally when a bar becomes vertically unstable and buckles, redistributing stars into a thicker central configuration. This process does not require a major merger at the time of bulge formation, though mergers may still contribute to the broader history of the inner galaxy. Instead, it is an example of secular evolution, the slow internal reshaping of a galaxy by its own gravitational dynamics. In the Milky Way, this idea gains strong support from stellar surveys and infrared observations, which reveal asymmetries and split structures in the central region consistent with an X-shaped or peanut-shaped bulge. The stars there are not arranged as a simple smooth sphere. They occupy a more elaborate geometry one that links the bar and bulge into a single evolving inner system. The bulge is densely populated, containing stars of many ages, though dominated by old populations. These stars crowd together far more tightly than stars in the solar neighborhood, creating a complex and luminous inner environment where orbits are diverse and line-of-sight confusion is severe. Dust between the Sun and the galactic center obscures much of this region in visible light, which is why infrared surveys are essential. Infrared wavelengths can pass through dust more effectively, allowing astronomers to map the distribution of stars and infer the bulge's true shape. Red clump stars, again, prove especially useful because their brightness helps estimate distances, and their distribution reveals the three-dimensional structure of the bulge with surprising detail. When these stars are counted across different lines of sight, the central region shows the signature of an X-like arrangement, a natural consequence of the bar's vertically thickened inner orbits. This is one of the clearest cases in which the Milky Way's hidden structure becomes visible only through indirect but consistent evidence. The bulge also preserves some of the galaxy's oldest stars, making it important not only dynamically but historically. Many bulge stars are metal-rich, reflecting intense and early star formation that rapidly enriches the inner gas. Others are more metal-poor and may belong to older populations or distinct components within the central region. The bulge is therefore chemically mixed, though not at random. It contains gradients and subpopulations that suggest that inner Milky Way forms through both rapid early activity and later internal restructuring. Some stars likely form during an early burst when gas is dense and conditions favor quick enrichment. Others are rearranged from the inner disk by the development of the bar and its thickening into a boxy bulge. This means the bulge is not easily reduced to one origin story. It may contain a smaller classical component produced by early collapse or mergers overlaid by a much larger bar-related bulge produced through secular evolution. The balance between these components remains an area of active research, but the main conclusion is secure. The central swelling of the Milky Way is structurally and historically composite, not a single uniform object. The motions of stars in the bulge are correspondingly complex. Some follow bar-related elongated orbits. Others move in more random directions, especially if they belong to older and dynamically hotter populations. Measuring these motions is difficult because the region is crowded and distant, but spectroscopic surveys and long-term observations have provided increasing detail. These data help test models of the bulge's formation, showing which stars rotate in step with the bar and which do not. Rotation is strong in much of the bulge, supporting the idea that bar dynamics are central to its present form. If the bulge were mainly a classical merger-built spheroid, its motion would be expected to differ more strongly from the patterns seen in the rotating bar. Instead, much of the evidence points to a close kinship between the two. The bulge is in a real sense the inner bar made thicker and more vertically extended, while still carrying older stars from the galaxy's earlier history. Gas and dust are present in the inner galaxy as well, though distributed differently from the outer disk. Dense clouds and active star formation occur in the central molecular zone, a region close to the center, where conditions are extreme compared with the solar neighborhood. Temperatures, pressures, magnetic fields, and turbulent motions can all be higher there. This does not make the bulge itself a starburst in the present era, but it does mean the inner few hundred light-years are active in ways distinct from the broader bulge. The central region is therefore layered even within itself with old stellar populations, bar-supported orbits, dense gas concentrations, and the still deeper influence of the galactic center, all packed into a relatively small volume. The peanut-shaped bulge is the Milky Way's inner body made visible through geometry. It shows that the galaxy's center is not round in the simplest sense, nor built only by ancient violent events. It is also shaped by slow internal motion, by a bar that thickens and lifts its own inner stars into a vertically structured form. In this dense and crowded region, the Milky Way carries both memory and motion together. Ancient stars remain, but they are arranged by later dynamics into a shape that no early observer could have guessed from the night sky alone. The bulge is therefore not just a concentration of stars. It is a signature of how the inner galaxy evolves, revealing that even at the center long time and repeated orbital influence can sculpt matter into forms at once stable, crowded, and unexpectedly intricate. At the center of the Milky Way, hidden behind dust, crowded by stars, and buried within the dense inner regions of the bulge, lies one of the strongest known gravitational sources in the galaxy. This object is Sagittarius A, the compact radio source identified with the Milky Way's supermassive black hole. It does not shine like a star, and for most of human history, nothing in the night sky suggests its presence directly. Yet its existence is supported by some of the most precise and compelling evidence in modern astronomy. Near the galactic center, a small group of stars moves at extraordinary speed around a point that emits very little visible light. Their orbits are not vague drifts. They are measurable paths traced across years and decades with enough precision to reveal the mass concentrated at their center. The conclusion is that several million times the mass of the Sun is confined within a region smaller than the orbit of Mercury around the Sun. No stable cluster of ordinary stars, white dwarfs, neutron stars, or other known compact objects can account for such a dense and dark concentration. The best explanation, consistent with both theory and observation, is a supermassive black hole. A black hole is a region where gravity becomes so intense that within a certain boundary called the event horizon, nothing can escape, not even light. Outside that boundary, however, the black hole can still influence nearby matter through ordinary gravity, and it is this influence that makes Sagittarius A detectable. The clearest evidence comes from stars very close to the center, especially one known as S2. This star follows an elongated orbit that carries it remarkably near the central mass, completing a full circuit in about 16 years. As it approaches closest passage, its speed rises to several thousands of kilometers per second. Its motion matches the expectations of a compact gravitational source of about 4 million solar masses. Other stars in the same region show related behavior together, forming a precise dynamical map of the central mass. These observations, carried out over many years by teams using powerful telescopes in Chile and Hawaii, provide one of the most direct demonstrations that a supermassive black hole occupies the Milky Way's center. They also allowed tests of general relativity, Albert Einstein's theory of gravity, in a regime much stronger than what can be examined within the solar system. Measurements of orbital precession, the slight rotation of an orbit over time and shifts in the star's light, caused by the black hole's gravity, both support the relativistic description. In this way, the galactic center becomes not only a location in the Milky Way, but also a laboratory for fundamental physics. Sagittarius A* is relatively quiet compared with the supermassive black holes in some other galaxies. In active galactic nuclei and quasars, black holes can consume large amounts of gas and radiate enormous energy across the electromagnetic spectrum, sometimes outshining the galaxies around them. The Milky Way's central black hole is much less luminous. It is often described as quiescent, which, in this context, means that it is accreting matter only at a low level. Gas and dust do fall toward it, but most of the available material does not cross the event horizon efficiently. Much of the energy that might be released during accretion is not radiated in the same way it is in more active systems. As a result, Sagittarius A* appears faint compared with what its mass could in principal power. This apparent quiet does not mean the region around it is empty or simple. The environment near the black hole contains hot gas magnetic activity and occasional flares seen in infrared and X-ray wavelengths. These flares likely result from turbulent plasma and magnetic reconnection events in the inner accretion flow, though the exact details remain under study. The central black hole is therefore silent only in relative terms. It remains active on small scales, even if it is not currently feeding at the dramatic rates seen in brighter galactic nuclei. One of the most remarkable achievements in recent astronomy is the imaging of the shadow of Sagittarius A* by the Event Horizon Telescope, an international network of radio observatories operating together as a virtual Earth-sized instrument. This effort does not produce a conventional photograph. Instead, it reconstructs an image from radio waves emitted by hot material very near the black hole. The resulting ring-like structure with a darker central region is consistent with the predicted appearance of light bent and partially captured around a supermassive black hole. The image is challenging because Sagittarius A* varies rapidly, and the surrounding material changes on short timescales compared with the observation process. Even so, the result provides another line of evidence linking the compact radio source to a black hole of the expected mass. Together with the stellar orbit measurements, it strengthens one of the clearest conclusions in galactic astronomy. The Milky Way's center contains a true supermassive black hole, not merely a dense star cluster or an unresolved mystery. The presence of Sagittarius A* also affects the immediate stellar environment. Very close to the center, stars orbit in a powerful gravitational field that can stretch, perturb, or even disrupt objects passing too near. Gas clouds approaching the center may be torn apart or heated intensely. The distribution of stars in the innermost region reflects this influence. Though the exact formation and survival of stars so near the black hole remain areas of active research, observations indicate that some young massive stars exist surprisingly close to the center, raising questions about how star formation proceeds in such an extreme environment. It remains uncertain whether these stars form in place under unusual conditions or migrate inward from somewhat larger distances. Either possibility reveals that the galactic center is more complex than a simple dead zone around a dark object. Gravity dominates there, but matter still responds in varied and dynamic ways. The black hole also matters beyond its immediate surroundings, because it anchors the deepest part of the Milky Way's gravitational well. It is not the whole story of the galaxy's mass or structure, far from it, since the disk bulge and dark matter halo together contain vastly more total mass spread across much larger scales. but as the central singular concentration, Sagittarius A*, gives the inner galaxy a focal point of extraordinary density. It is the hidden center in the strictest sense, not just the middle of the visible band, but the point around which the innermost stars circle at enormous speed. For centuries, the Milky Way is known as a river of light. Only recently does it become clear that at the center of that river lies a darkness so concentrated that it bends light itself, holds millions of solar masses in a tiny volume, and reveals its presence only through the motions of nearby stars and the subtle glow of matter falling toward the edge of no return. Although Sagittarius A* is quiet in the present era, the central regions of the Milky Way preserve signs that this calm has not always defined the galaxy's inner life. Above and below the galactic center, extending tens of thousands of light-years into the halo, astronomers have discovered immense paired structures known as the Fermi bubbles. These giant lobes emit high-energy gamma rays and also appear in X-ray and radio observations, forming two vast hourglass-like outflows, rising in opposite directions from the core. Their symmetry is striking. They are centered closely on the inner galaxy and stand almost perpendicular to the disk, as though some major release of energy once erupts from the central regions and drives matter outward into the surrounding halo. The bubbles are not small local features. They rank among the largest coherent structures associated with the Milky Way's center, and their existence shows that the present quiet state of Sagittarius A* does not tell the whole story. At some time in the past, the inner galaxy appears to have been much more active. The precise cause of the bubbles remains under study, but the leading explanations involve either a past episode of heightened accretion onto the central black hole, or a burst of intense star formation near the galactic center, or perhaps a combination of both. In the first case, Sagittarius A* would once have consumed gas at a much higher rate than it does now, releasing energy through jets or winds that inflate the bubbles into the halo. In the second, many massive stars forming in the inner region would live short lives and explode as supernovae, driving a large-scale outflow of hot gas. Both mechanisms are physically plausible, and both are known in other galaxies. Observations indicate that the bubbles contain very energetic particles and hot gas, but it remains uncertain exactly how much of the total structure is powered by black hole activity versus starburst activity. What is clear is that the Milky Way's core is capable of influencing regions far beyond the central few light years. Energy released near the center can shape the lower halo on scales visible across a large fraction of the galaxy. This changes the sense of the Milky Way as a calm, slowly turning disk. Hidden within that long-term quiet are episodes of forceful central release. The discovery of the Fermi bubbles comes from gamma-ray data collected by the Fermi Gamma-Ray Space Telescope, which reveals two large lobes with relatively sharp edges. Their shape suggests a significant injection of energy rather than a diffuse background process spread evenly across the halo. Subsequent observations at other wavelengths strengthen the picture. X-ray emission traces hot gas around or within the bubbles, while radio features indicate magnetic fields and cosmic ray electrons moving through the outflow. Together, these signals imply that the bubbles are not simple empty cavities, but structured energetic volumes filled with particles and fields shaped by past central activity. Their age is still estimated rather than known precisely, but many models place their origin within the last several million years, a recent interval on galactic timescales. That is long before human astronomy, but short compared with the Milky Way's age of more than 13 billion years. In this sense, the bubbles are not ancient scars from the galaxy's youth. They may be traces of comparatively recent unrest. Other evidence also hints that Sagittarius A asterisk is more active in the past than it appears now. Astronomers observe X-ray echoes in nearby molecular clouds, especially in the central molecular zone, which suggests that the black hole may have flared much more brightly in the recent past. These echoes occur because X-rays emitted during an earlier outburst travel outward and are later reflected or reprocessed by dense clouds, allowing a delayed record of the event to be seen. Since the distances to the clouds are large, the light takes years to centuries to arrive and scatter toward Earth. By studying changes in these reflected signals, astronomers can infer that the central source is once significantly brighter than it is today. This does not imply a quasar-like phase equal to the brightest galactic nuclei, but it does suggest that the present state of very low activity is not permanent. Sagittarius A asterisk may pass through varying levels of accretion depending on how much gas becomes available and how efficiently it reaches the inner region. The black hole's apparent silence is therefore best understood as one part of a changing cycle, not as a fixed trait. The central molecular zone, dense with gas clouds, turbulence, and star formation, provides the raw material that could intermittently feed either a starburst or the black hole itself. This region differs sharply from the solar neighborhood. Gas densities are higher, motions are more extreme, magnetic fields can be stronger, and clouds are subject to intense tidal forces from the deep gravitational well. Under such conditions, ordinary ideas of cloud collapse and star formation must be adjusted. Some young, massive stars and clusters do form there, but the environment is harsher and more compressed than in the calmer outer disk. If enough gas accumulates and loses angular momentum, part of it can move inward toward the black hole. If, instead, it forms stars, efficiently stellar winds, and supernovae can help drive hot gas outward. In either path, the central region becomes a source of feedback into the surrounding galaxy. The outflow of energy and matter from the core may affect gas in the halo, alter pressure conditions above and below the disk, and participate in the longer circulation between disk and halo. The exact strength of these effects over time remains uncertain, but the principle is established. The Milky Way's center is not isolated from the rest of the galaxy. It can push outward as well as draw inward. The idea of ancient violence at the center should not be misunderstood as continuous catastrophe. The evidence does not suggest that the Milky Way is now in a state of severe disruption, nor that the central black hole regularly threatens the entire disk in dramatic fashion. Rather, it suggests intermittent activity episodes of enhanced outflow or radiation separated by longer quiet intervals. This pattern fits what is seen in many galaxies, where central black holes and inner star-forming regions vary over time depending on fuel supply and local conditions. The Fermi bubbles and X-ray echoes are therefore echoes of process, rather than signs of present turmoil. They show that the calm view of the Milky Way is incomplete unless it includes the possibility of energetic central phases. Even a galaxy that now appears serene can carry recent evidence of outbursts large enough to shape regions far above and below its plane. In the deepest part of the Milky Way, gravity gathers matter, but not all of that matter stays confined. Sometimes energy drives it back out, inflating bubbles into the halo and leaving high-energy traces that remain long after the original event subsides. The galaxy's core quiet in the present moment still carries the memory of these buried surges. The evidence is written in giant lobes, reflected X-rays, and hot central gas, all pointing to a truth that the visible night sky cannot show. The Milky Way's center is not only dark and massive. It is also a place with a history of release, where even silence turns out to be the afterstate of earlier force. Even at this inward end of the journey, with the bulge and black hole now in view, the Milky Way does not resolve into a finished object. It remains a galaxy, still changing, still gathering, still carrying unresolved structures and future transformations within it. The clearest lesson of its history is that it is not static. It forms through repeated assembly, internal rearrangement, chemical recycling, and long interaction with its surroundings. The halo preserves the remains of captured dwarf galaxies. The disk continues to shape stars from cooling gas. The bar channels material inward. The center records both silence and earlier outflow. Across all of these regions, the Milky Way appears less like a completed architecture and more like a living system in slow evolution. It is stable enough to endure for billions of years, yet open enough to remain unfinished. One sign of that incompleteness is the continued presence of satellite galaxies around it. The large and small Magellanic Clouds, visible from the southern hemisphere, are the most obvious nearby companions, but they are not the only ones. The Milky Way is surrounded by a retinue of dwarf galaxies, some bright enough to have been known for centuries, others so faint and diffuse that they have only recently been detected through modern surveys. These companions orbit within the larger dark matter halo, and their futures are shaped by the Milky Way's gravity. Some may survive for long times on wide paths. Others may be stripped, disrupted, or eventually absorbed, adding stars and dark matter to the outer halo. This process is not merely a relic of the past. It continues in the present era. The Milky Way is still accreting small systems, still gaining mass in pieces, still reshaping its outskirts through tides and mergers. The galaxy is therefore not isolated in any final sense. It is part of a local environment in which matter still moves between systems over vast spans of time. Gas inflow is another sign of ongoing development. The Milky Way continues to require fresh material if it is to sustain star formation over billions of years. The gas now present in the disk would gradually be consumed or locked into stars and stellar remnants, if not replenished in some way. Observations indicate that inflowing gas exists in the halo and in high-velocity clouds, some of which may represent material falling toward the disk from the surrounding environment. Some gas may originate in galactic fountains, rising from the disk after heating and later cooling and returning. Some may come from interactions with satellite galaxies. Some may come from the broader intergalactic medium drawn inward along the larger-scale structure of the universe. The exact balance among these sources remains uncertain, but the implication is strong. The Milky Way sustains itself not by using a fixed supply once and for all, but by participating in continuing exchange with its surroundings. The galaxy remains open. It loses matter through winds and outflows, but it also gains matter from outside. This exchange supports the long continuation of star formation in the disk and keeps the galaxy from becoming entirely dormant. Not all matter entering the galaxy becomes part of a star or planet in an orderly way. Some may remain as diffuse gas. Some may form brown dwarfs, substellar objects, too small to sustain stable hydrogen fusion. Some may become planets that never settle into a traditional planetary system. Observations in recent decades suggest that free-floating planetary mass objects exist bodies that wander through interstellar space without orbiting a star. These are often called rogue planets, though their exact origins may differ. Some may form in a way similar to stars from collapsing gas clouds, but at much smaller mass. Others may begin in planetary systems and later be ejected through gravitational interactions. The Milky Way may contain large numbers of such objects hidden because they are faint and cold. They are part of the galaxy's unseen population, not dominant in mass like dark matter, but significant as a reminder that galactic evolution produces more than neatly ordered stars with stable families of planets. It also produces drifters' remnants and bodies displaced from the systems in which they begin. Their existence fits the broader character of the Milky Way as a place of partial order rather than perfect arrangement. Even on the scale of the whole galaxy, one future event stands out with unusual clarity. The Milky Way and the Andromeda galaxy are moving toward one another and are expected to interact several billion years from now. Andromeda, the nearest large spiral galaxy, is already part of the same local group of galaxies. Measurements of its motion indicate that it approaches rather than recedes. Over immense timescales, the two galaxies are likely to pass through one another, distort each other through gravity, and eventually merge into a larger system. This will not resemble a simple collision of solid objects. The stars are so far apart that direct stellar impacts are unlikely, but gravitational tides will reshape both galaxies profoundly. Gas clouds may compress and trigger bursts of star formation. Orbits of stars will be redistributed. Spiral structure may be destroyed and replaced by a more rounded or elliptical remnant. The solar system, if it still exists in recognizable form at that far future time, would likely survive the merger as a gravitational participant, though it could be moved to a very different orbit within the combined galaxy. This future merger is a continuation of the same process that built the Milky Way in the past. What the galaxy once does to smaller companions, it may later experience with a neighbor closer to its own scale. The Milky Way's story is therefore not only backward-looking, it extends ahead into further transformation. This unfinished quality applies also to knowledge itself. Even with modern surveys, powerful telescopes, radio arrays, and theoretical models, major uncertainties remain. The exact shape and mass of the dark matter halo are still being refined. The detailed history of some mergers is still being reconstructed. The formation pathways of the bulge, thick disk and bar continue to be tested against new data. The role of feedback in regulating star formation is still debated in specifics. The origins and abundance of rogue planets remain only partly known. Even the central black hole, though strongly established, still raises questions about its feeding history and present environment. The Milky Way keeps secrets, not because it hides them deliberately, but because it is large-layered, dusty dynamic, and only partly visible from the place within it where human beings happen to live. To understand it is to accept an incomplete but growing map. The galaxy that arches across the night sky as a band of soft light is, in reality, a structure of collisions: invisible matter, chemical memory, stellar birth, central gravity, and future merger. It is neither serene in the simple sense, nor chaotic without form. It is something between a long evolving system that carries order through motion and continuity through change. The Milky Way remains unfinished because galaxies are not monuments. They are processes extended across billions of years. Ours is no exception. It grows by absorption, renews itself by recycling, holds hidden populations in darkness, and moves toward transformations not yet complete. Its greatest secret may be that it is not a thing to be solved once and for all, but an ongoing history in which stars' gas dust, dark matter, and time continue to shape one another inside a structure that is already ancient and still becoming itself. The Milky Way now settles back into quiet scale, no longer as a bright band overhead, but as a vast structure held together by time, gravity, and memory. Its outer halo keeps the record of ancient fragments. Its dark matter scaffold extends beyond sight. Its disk bends, turns, and forms stars from cold hidden clouds. Its spiral arms gather light without ever truly standing still. Its central bar and bulge reshape the inner galaxy slowly, while the black hole at the core waits in near silence, carrying the possibility of motion and release. Across every region, the same pattern remains. Matter drifts, collects, ignites, disperses, and returns. Nothing in the galaxy is fixed forever, yet almost everything endures long enough to seem still. From within one small spur of one spiral galaxy, the whole appears both intimate and unreachable, familiar in the night sky, and immeasurable in reality. Ancient stars preserve the chemistry of early cosmic time. Stellar nurseries prepare future suns and possible worlds. Captured galaxies dissolve into streams. Invisible mass continues to hold the larger form in place. Even the future is already moving slowly toward new mergers and new rearrangements. The Milky Way becomes in the end less a single object than a long unfolding balance between structure and change. It is a home, but also a process, a pattern, but never a finished one. In that slow, unfinished turning, the galaxy offers no final edge, only deeper layers of quiet motion, each one receding into darkness, each one carrying traces of what came before, and each one continuing onward through the patient, silent flow of cosmic time.